In this webcast, we're going to take a look at a different kind of addition to carbonyl compounds that occurs when the carbonyl group is conjugated to a carbon-carbon double bond. When this is the case, there are two electrophilic sites in the entire pi system of the alpha-beta unsaturated carbonyl compound. So if you look here, you can see that resonance structures will reveal the two electrophilic sites. Pushing electrons to the carbonyl oxygen reveals that the carbonyl carbon, the traditional electrophilic carbon, is still electrophilic in the alpha-beta unsaturated carbonyl. However, because this pi bond is in conjugation with the carbonyl group, we can push electrons once more, and this reveals that the terminal carbon of the double bond is also electrophilic. This opens the door to two possible addition pathways: the direct or 1,2 addition pathway, which is the addition mechanism that we've seen in the past few webcasts, and the 1,4 or conjugate addition pathway, in which the nucleophile adds to the terminal carbon of the double bond, leaving the carbonyl group intact. The elementary step ADN also applies to polarized carbon-carbon double bonds, not just to carbon-oxygen double bonds. In the case of the alpha-beta unsaturated ketone, ADN to the carbon-carbon double bond corresponds to conjugate or 1,4 addition. The arrows for this process are exactly analogous to those for direct addition. The nucleophile adds to the more electron-deficient terminal carbon, and the double bond is pushed onto the more electronegative carbon attached to an electron withdrawing group, which can stabilize the resulting negative charge. If you take a look at the LUMO for an alpha-beta unsaturated carbonyl compound, notice that the terminal carbon makes a substantial contribution to the LUMO orbital density, and so comparing the carbonyl carbon with the terminal carbon of the alpha-beta unsaturated ketone, we see it's not surprising that nucleophiles can add either to the terminal carbon or to the carbonyl carbon. As was the case for direct addition, conjugate addition can proceed by one of two mechanistic pathways depending on the pH of the medium in which the reaction is run. If the reaction is run with a strong nucleophile under basic conditions, then addition of the nucleophile to the alpha-beta unsaturated ketone will occur before protonation. In this case, we have the top pathway, in which the nucleophile adds via an ADN-type step to generate an enolate anion, in which a negative charge is adjacent to the carbonyl carbon. Protonation of the enolate anion through the introduction of H+ leads to the product in which nucleophile and hydrogen have added across the former carbon-carbon double bond. Under acidic conditions, protonation will be very fast and very easy, and will occur before addition of the nucleophile, which is typically weak under acidic conditions. Protonation of the carbonyl carbon, which is again the most basic site in the alpha-beta unsaturated ketone, leads to an intermediate in which the LUMO energy has been lowered. Addition of the nucleophile is then made much easier, and after the nucleophile adds to the terminal carbon, just as it did in the top case, we're left with what's called an enol. It's called an enol because there's a carbon-carbon double bond attached to an alcohol functional group. A so-called tautomerization of the enol, which really just moves this hydrogen from oxygen to carbon, then regenerates the carbonyl functional group.